Good morning. We're going to continue on with counting techniques. Today is not about probability. Today is about counting techniques. And we're going to go over one of the really simple rules having to do with unions. So what if I said something like this? Let's say 70% of Mesa students enroll in math, and let's say 60% of Mesa students enroll in English, and let's say just, I don't know, how about 40% of students enroll in both. Okay. Now, when I say 70% enroll in math, that doesn't mean they enroll in math and nothing else. I just when you look at Mesa student body, we're saying 70% are enrolled in a math class. Same student body, 60% are enrolled in an English class. Same student body, 40% are enrolled in both. The question is, what percent is in at least one of the courses? Well, one thing we know about probability is probability cannot exceed 1. So if I said, well, if 70% of the people are in math and 60% in English, then 130% of the students are in, wait a minute, that doesn't make any sense. I can't have 130%. That doesn't make any sense. That no work, as my wife would say, that no work. So how do we do this? Well, the simplest way, you got the numbers now. Simplest way is with the Venn diagram. So let's do this as events. So let's say event A is a student enrolls in math. Let's say event B is a student enrolls in English. Okay, so with that said, then the probability of A is simply 0.7. The probability of B is simply 0.6. Okay, that makes it easy. But what do we say about the students who are enrolled in both simultaneously? Oh, that would be A and B. If you're enrolled in A and B at the same time. Well, let's look at it from a Venn diagram point of view. Okay, this might make it easier to conceptualize. There's math, there's English. Now, are there students who aren't enrolled in either one? Of course. So do I do it like this? Okay, oh, that must be the people that are enrolled in math and English. Okay, so you're enrolled in math, you're enrolled in English, and you're enrolled in both. All right. Does anybody, oh, by the way, and then we'd have to figure out what goes out here. Does anybody have a problem with my picture? Please say yes. Does anybody have a problem with this picture?
Yes.
Good. What's the problem? Probabilities kind of have to add up to what?
1.
What are they adding up to so far? 1.7. That's worse than it was before. There's something terribly wrong. One of those three numbers is correct. Which one is correct, by the way? Only one of them is correct.
The center one?
The center one. Yeah, this is the 40% that are enrolled in both. Why is this one wrong? I didn't say 70% are enrolled in math and not in anything else. We said 70% are enrolled in math. So 70% make up this circle. Therefore, what's going to go out here?
30%.
Yeah, I'll put my zeros there. Oh, now 70% are in the math circle. So this can't be 0.6. There's going to be 60% of the people in this circle. So the probability of being on here must be 0.7. 2. Now you can see that, oh, okay. So now how many people are here?
90%.
That's only 0.9. So that means there's going to be a 0.1 out here. Now my picture is now correct. So A and B would be equivalent to saying intersection in this case. Okay, you're simultaneously enrolled in math and English. So that means you're in the intersection of the two circles, and that's extremely important. So the last piece would be, what's the probability of being in the intersection? And that's the 0.4. Now, my question was, how many students are enrolled in at least one of them? Well, I think we all see the answer, or 90% of the students are enrolled in at least one of them, because there's 10% of the people that aren't enrolled in anything. Okay, but 90% are enrolled in at least one of them. So where do I get the 0.9 from these numbers? Well, clearly it's going to be this plus this minus this. So this leads to a very, very important formula. Let me go ahead and erase this. And this is for unions, okay? For events A and B, the probability of being, oh, I'll do this on the next line, sorry. The probability of a union is the probability of A plus the probability of B. That's always true, but the problem is when I added up those two individual probabilities, it exceeded 1 this time, minus the probability of the intersection, because the intersection would be double counted. A intersect B is part of this, A intersect B is part of this, and so I would have been counting these people 2 different times if I simply added those 2 up. So when we subtract the intersection, that way we don't double count. So my picture made it really, really clear. But this is a very, very powerful formula. Now, first and foremost, you cannot calculate an intersection. I'm amazed at how often, and especially people who have had statistics and they do a lot of this stuff, you cannot calculate an intersection. An intersection has to be, I can just simply count it or I'm told it. But a lot of people will try to calculate an intersection by multiplying and dividing and doing all sorts of crazy stuff. No, I told you the intersection was 0.4. That couldn't be calculated. Okay, there's no combination of numbers that I would multiply or manipulate. And I'm always amazed at how many people say, no, I learned in my class you calculate it this way. Well, no, that's not true. Yeah, no. I've taught statistics for 30 years. You can't calculate an intersection. Now, intersections, when I say calculate, I mean, you're not going to number crunch. I can look and physically see what's in my intersection, just 1, 2, 3, 4, 5. I can count an intersection. That's not a calculation. That's not the same thing. So given this, what if I got this? What if I have 2 sets that do not intersect? Now, there's 2 words or 2 terms that kind of mean the same thing, but they're used in a different context. If A and B are sets, forget probability, forget all of this. A and B are just 2 sets. A might be the set of names that are in my Math 245 class, and B might be the set of names that are in my Math 150 class. Okay, there are no names that are in both classes, by the way. We'd say in this case, if A intersect B is the empty set, then A and B, the word is disjoint. When 2 sets have no intersection, the sets are disjoint, and therefore the probability of being in the intersection would be 0. If A and B are events, like I might be flipping a coin and counting the number of heads or something, A and B are events. They're things that can be measured and counted, and probability can be taken. If A and B are events that have no common outcomes, okay, I listed all the outcomes of A, I listed all the outcomes of B. So I'm not thinking of them as just sets. Now I'm thinking of them as part of a probability experiment thing. Then we'd say that A and B are, and the term now is mutually exclusive. I can't spell. mutually exclusive. Okay, mutually exclusive events. Two events are mutually exclusive if the list of elements as sets are disjoint. So mutually exclusive, disjoint basically mean the same thing, but it's a context thing. I use mutually exclusive when I'm talking about the events in a probability experiment. I use disjoint if I'm just talking about I have a list, and there's no overlap. So you can see how the nomenclature there is slightly different, but they basically mean the same thing. So going back to the statement here, if the events are mutually exclusive, that would mean that this quantity right here would be 0. Therefore, this is a very simple way to measure whether two events are mutually exclusive. If the probability of the union is simply the sum of the two probabilities, that means there's no intersection. Okay, so that's a really, really easy way to measure it. Never assume there's no intersection. Always assume there's an intersection and then do this. And then if it turns out there's no intersection, life is easy. But if there's an intersection and you didn't count it in your calculation, then you're in trouble, because then you're going to get perhaps even impossible values. You might get probabilities that are greater than 1, like in this case. Big yikes. Okay, so that's a fairly simple thing. So when asked what's the probability of a union, you just take the sum of the individuals. Now, if I have 3 or more, it gets kind of complicated. I'm not worried about 3 or more right now. Let's just concentrate on 2 things. Okay, so I've got the probabilities of unions. How do I know it in words that that's what I'm asking? Well, an intersection is when I'm in A and I'm in B at the same time. So the key word there is and. A union is if I'm in A or I'm in B. So if I said, what's the probability of A or B occurring, that would be a union. Okay, that's the easiest way of doing it. And some people will write the formula literally with the word A or B, and that's okay. There's nothing wrong with that. Now, with that said, I want to talk next about complements. Complements are one of the most powerful and important parts of counting techniques. Now, remember that the idea of a complement, okay, the complement is everything else. So if I have a full glass of water, the complement is not full. So the key always was putting the word not in front. So if I'm talking about outcomes of an experiment and I have a finite list of possible outcomes, then when I'm asking for a particular type, the complement would be, of course, everything else. Now, the notation used for complements changes from textbook to textbook. It doesn't really matter, by the way. But if I said I have event A, then the complement, there's 2 ways you'll see it in a textbook. The complement, either we would put a bar over the top or we would use a complement. I'm okay with both of these. If I'm talking about a statement, a logical statement, then the complement is generally the squiggle, which means in this context, not. But we don't say not for events. That doesn't make any sense, right? An event is a list of outcomes. You don't say not the outcomes, you say all the other outcomes. So either one of these notations is totally acceptable. Just be consistent. One textbook to the next, they'll change. I like this one just because it reminds me it is complement, but this one's also okay. Okay, and the concept here is this. If I have a finite set, I have A and A complement. If our universe, our universal set, right, we call that the sample space, then we say that A union A complement is the sample space. A intersect A complement is the empty set. That's absolute. That's what it means to be a complement. Together they make up the whole, but there is no overlap. Now, the reason complements are so incredibly powerful is from a probability standpoint. If there is no intersection, then the following must be true. The probability of A plus the probability of A complement has to equal 1. That's an absolute. The probability of A and the probability of A complement must equal 1. Okay, now think about that for a minute. Whenever you're asked to calculate a probability of something, you calculate the probability straightforward. But what if what if the calculation of the probability is really long and cumbersome, and basically most of the outcomes are what you're counting? Well, it turns out sometimes it's much easier to calculate A by first calculating complement. I'll give you a really simple example. We did dice rolls last day. I'm going to roll the dice and then I'm going to add up the total. And I want to know, what is the probability that my outcome had a sum of 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12. So you calculate the probability of a 3, add that to the probability of 4, all the way through to a 12, because all of these would be mutually exclusive. There are no outcomes where the dice add to 3 and also add to a different number. So dice rolls are really nice. So you calculate all those individual probabilities and you add them up. I just said, what's the probability of having a sum between 3 and 12? I only excluded a sum of 2. There's only one way to get a sum of 2. So if I wanted the probability of, let me write it this way, sum of at least 3. That's what I just asked you. 3 or 4 or 5 or, well, if the only thing I'm excluding is a 2, this would equal 1 minus the probability of a sum of 2, which would be 1 minus 1 over 36 or 35 over 36. To calculate each of them and add them up is absolutely correct. But it was a heck of a lot easier if I just said, well, what am I not including? Okay, I'm not including the one total that adds up to 2. There's a 1 in 36 probability of getting that total. So what I'm asking is everything else, 35 out of 36. If calculating the probability of a complement is easier than the probability of what you're asking, then you would always do it this way. If calculating the probability of what you're asking is straightforward, then just do that. It never matters, but complements sometimes are easier to calculate. Again, if what you're asking for is most of the outcomes, the complement may be significantly easier. So we have this really simple concept here of complements. Now, I want to do something and I want to do it repeatedly. So one of the classic ones is that you have what they call earn problems. Now, I always laugh because in probability in general, this is considered a classic problem. I have an urn filled with, let's say, colored marbles. Now, why an urn? I don't know why we always use an urn. I always think of an urn as something that you put somebody's ashes in after they're cremated. I'm not joking. That's the only use of an urn I've ever heard in my life, except in probability. In probability, everything comes from an urn, which is kind of odd that you would do that. So I have an urn. It's a jar, it's a bowl, it's whatever you want to think of it as. And I'm going to have colored marbles in my urn. Okay. So let's say in my urn, I've got 4 red, 8 black, and about 6 white marbles. Okay. Now, they're all mixed. You can't see them. You're going to reach your hand in. You're going to select, let's start by, you're going to select 1 marble. Okay. Find the probability it is black. Let's start simply. Okay, this is trivial. So how do I do this? Well, my sample space consists of how many things? My sample space consists of 18 marbles. 8 of them are black. I can't see the marbles, they're all mixed around. So when I reach in and I pull it out, what would be the probability? Anybody want to try?
8 over 18.
8 over 18, yeah. Yeah, that's supposed to be simple. Now, I want to select more than 1 marble. Now, here's where it gets a little bit tricky. I want to select 2 marbles. Let's keep it real simple. Do I pick a marble up, look at it, put it back in, mix them around? Do I pick a marble up, look at it, set it aside, and pick a second marble? Do I grab 2 marbles simultaneously and pull them out and look at them? I just give you 3 different cases that are all different in how we view them. And this is kind of tricky. So there's words that we use. We're going to select 2 marbles. Now there's two possibilities. Okay, right now, let's say we're going to select our marbles one at a time. I'm going to select two marbles one at a time. But am I putting the marble back before I make the second selection? Or am I keeping the marble? That actually makes a lot of difference. So the terms we use are with replacement or without replacement. And these are very different because they will always give you different answers. With replacement is I look at my marble and I put it back in and I mix them around. So I have all of the 18 marbles on my second round. Without replacement means I look at my marble, I set it aside and I go select another marble. So I'm going to pick two marbles. Okay, I want to find the probability that both are black. Well, there's two different possibilities, with replacement, without replacement. So let's first start with replacement. I pull a marble out, I look at it, and you said the probability that it was black was 8/18. That doesn't change. Okay. I put the marble back, and now I'm going to select another marble. What's the probability that second marble is black?
8/18.
8/18. So this is my answer. Reduce it if you can. That's my answer. Now, in the second case, I pulled the marble out, I looked at it. It was black. Now I'm putting it back in. Excuse me, I'm not putting it back in. Sorry, I'm setting it aside. What's the probability the next choice is also black?
7/18.
7/17.
How do we decide? I removed one of them from my sample space. So my sample space now has only 17 marbles, but it only has 7 black marbles because I've already selected. Remember, we're asking, I'm saying I'm going to select 2 black ones in a row. This start 17. This is not the same answer. With replacement, without replacement gives you different answers. Oh, because I've changed the sample space. That's key. Now, if I kept going and said, what's the probability I keep going and selecting black marbles? Won't there be a point when there's no more black marbles? So if I kept going, eventually there's going to be 0 black marbles. And so if I said, what's the probability that I select 13 black marbles in a row without replacement? Well, it'd be 0 because I don't have 13 black marbles to select. Oh, now this same idea applies when you play cards. So if anybody here's ever played cards, I don't care if you're playing Go Fish, I don't care if you're playing poker or blackjack, any form of card game, when you have your cards, that means they're not in the deck of cards anymore. They're in your hand. So if I said, I have an ace of spades, I'd like to get another one. Well, you can't, you already have it. Okay, there's a limited selection here. So if you're playing cards and you're dealt the cards, everything here clearly is without replacement. Because once you have that card, it is no longer an option. Once you take that black marble out, that one's not an option anymore. So card games typically are without replacement in this sense. Okay. Now let's do an example with cards. Actually, I want to do one more example in this case. Sorry, I want to do one more because now I'm going to say, I want you to select 2 marbles, marbles with replacement. Okay. Find the probability that neither is black. Neither one of them is black. How do I do that? Well, how many not black marbles did we have? We had 18 marbles, 8 of them were black.
10.
There are 18 marbles, 8 of them were
10.
black, so 10. Do you agree? So I'm going to select a not black marble. What's the probability?
10/18.
I said with replacement. So what's the second choice going to be?
The same thing.
The same thing. Oh, now if I said without, I'll just write it like that, without replacement, what would that be?
10/18.
You're getting 2 marbles in a row.
9 out of 17.
9/17. Again, it changes. So the with and without is really, really important. Now it's not complicated. You got to read, oh, I'm doing this with replacement, I'm doing this without replacement. Now, what's really interesting is in the real world. Okay, I'm going to use a statistical example. When we're doing sampling in the real world, okay, a typical one that most people are familiar with are any form of polls. Okay, right now the sampling might have to do with people getting vaccinated, and I'm going to randomly sample 100 vaccinated people and ask them about their side effects. It might be in an election time. I ask 100 people randomly, who did you vote for, or what did you vote for on this particular proposition? And I use sampling. Okay, if I do it right, the conclusions I make about the sample I can extend to the population if I do the sampling correctly. That's what you learn about statistics. Okay, it's very powerful if I do my sampling correctly and it's unbiased and all that kind of stuff. Now, the idea is when you're doing a sample and I'm randomly selecting people, it might be the person on the street. Is it physically possible I could ask the same person twice? Is that actually possible in a sample? Think about it. Yes or no? What do you think? Is it possible I could ask the same person twice if I'm doing this over a period of time, large geographic area?
Yes.
Yes. And guess what? In reality, we don't exclude that. We keep that as a possibility. In other words, I sample with replacement. When doing something called cluster sampling, which is a very powerful tool to determine things like endangered species, you take a map, you divide it into a grid. And the grid, let's say it's San Diego County, in my grid, I might have 1,000 little squares on my grid. And what you do is you randomly select the squares. You then literally search every square inch of that square for whatever it is you're looking for. It might be a particular insect. It might be a particular animal. It may, whatever it is you're looking for, you search that and you count it up. If you selected 3% of the grids and whatever number you get, you then extend that to all 1,000. That's your estimation. So when people say back in this particular year, we estimated there were this many, bald eagles or whatever. They didn't count every bald eagle in the United States. That's physically impossible. What they did was they did this cluster sampling. They used a grid and then they worked backwards. So if I said, I used 3% of the regions in San Diego County and I counted, 30, well, then just work backwards and say 30 is 3% of what? Of 1,000. Oh, okay. So that means I'm going to estimate there are 1,000. But in cluster sampling, and you're doing this, is it possible you counted the same species twice? Ooh, yes. That thing moved around, and later in the day, I'm in a different area and I end up counting the same thing. So if that matters to you and you do not want to count the animal or whatever you're counting a second time, what you do, and you've probably seen this before, I might be counting birds. I put a little tag on the bird. Maybe I put a little piece of tape or something on his leg, something that's not going to hurt him. That way, if I come across the same one again, I'm not going to count him because I already have. Okay, that's called tagging. But this is a very, very powerful way. But is it with replacement or without? So things like political polls, we don't care if we ask the same person twice. We work that in. That's not that big a deal if I'm asking a lot of people. All right. Now the last part of this that I want to do, and this is one of my favorites. Okay. If I was going to play a slot machine, okay, I'm bored. I go to one of the local casinos and I just do this all day. Make sure I always use the other arm. Otherwise, you can have a super developed arm. Okay. Well, the probability of winning at a slot machine is not very good. It's pretty terrible. But you're going to do it all day. It's a rainy day. You got a lot of nickels and you're just going to play the slot machine all day. And technically it's supposed to start over every time. The slot machine is not keeping score, right? It's sort of like when you flip a coin, the coin is not, okay, I did tails the last 3 times. I need to land on heads now. No, it doesn't work. Each time you do it, it's brand new. It starts over. So the question is this, if I know the probability of winning at a particular slot machine, it's going to be small. But if I play it a lot of times, can I calculate the probability of winning every single time? Can I calculate the probability of losing every single time? Can I calculate the probability of winning 10 times and 5 times? Yeah, every one of these probabilities can be calculated, but they are kind of complicated. But I want to talk about the probability of at least once. This is a very, very special kind of probability, and it's very, very cool to calculate. So you're going to play at a slot machine. Let's say a slot machine has probability, let's say, I'll keep it really simple, 1 in 10,000 of winning. Okay, let's keep it really small. Does that mean if you play 10,000 times, you're going to win? Anybody want to try that one? If I play 10,000 times, I'm going to win?
Not necessarily.
Not necessarily. By the way, I might lose every time. Is it possible I could play 10,000 times and win a lot? Many, many times? Is that possible?
Sure.
Because each time starts over. Oh, now there's something called expectation or expected value. Oh, okay. It'd be like saying if I flip a fair coin 100 times, I expect 50 tails. That doesn't mean I'm going to get 50 tails. It means 50 tails is the most likely outcome. It has the highest probability. That doesn't mean I'm going to. If I played this thing exactly 10,000 times, I expect that I'm going to win one time. I mean, that's the highest probability outcome, but it doesn't mean I will, and I still could win more than once. So here's the question. I want to play, let's say a slot machine has probability. You play, I don't know, let's say 5,000 times. Okay. You're really bored. You had a lot of nickels. Okay. I want to find the probability of winning. Now, if I pick any number of times, it becomes a very complicated calculation. It uses something called the binomial theorem, and it's actually not a trivial thing. We're going to do that later. But I want to of winning at least once. And that's the key. At least once means I win 1 or 2 or 3, all the way up to 10,000. Okay. Joseph, ask out loud if you.
I think I know how to do it.
Well, hold the thought then for just a moment.
Okay.
Now, there's only one assumption that's really, really critical here, and that is every time I play, it's a brand new game. When I said pick a card, any card from my deck of cards, and now you're going to pick a second card. Well, did I put the first card back? Because with replacement versus without replacement does change probability. But when I'm playing the slot machine, each time I pull the lever, think of the slot machine as it's resetting. Okay, it's resetting. When I'm shooting free throws, I'm an NBA basketball player and I'm shooting free throws. Whether I make or miss has no effect on my next free throw. The ball doesn't have a little computer chip inside and says, oh, I went in the hoop last time, so this time I must, the ball doesn't have memory. When you're flipping a coin, the coin doesn't have memory. When you're rolling the dice, every time it's a brand new thing. There's no with replacement or without replacement in this type of experiment. I just start over every single time. That 1 in 10,000 does not change based on what's happening. So the moment I win, it's still 1 in 10,000. If I lose, it's still 1 in 10,000. It doesn't, the slot machine doesn't say, well, this guy's played for a really long time. Maybe we should, throw him a bone and have him win a couple of times. Nope, it doesn't work that way. So the key is, what is the complement of at least once? We know this from earlier in the course. What's the complement of anything happening at least once?
Happening always?
Not happening.
Not happening at all.
Not happening at all. Yeah.
This is the equivalent of there exists means it happens at least once. And so remember, the negation of there exists means it always doesn't happen. So the complement of winning at least once would be never winning at all. Do you all agree with that? Hopefully. The complement of at least once. So let's say that A is, the event A is I win, okay, at least once. Then what would a complement be?
And no one.
Winning none of the times. Never winning.
Lose 5,000 times, but that's going to be a bad day. Okay. My question to you was, what is the probability of winning at least once? And I'm saying it's going to be 1 minus the probability of losing every time. Calculating the probability of winning at least once means I have to calculate the probability of winning exactly one time and then add that to the probability of winning exactly 2 times. And then add that to 3 times. And how many calculations would I do? 10,000 individual calculations. 1 win through 10,000 wins. We might be here a while, folks. So hope, get comfortable. Have lunch delivered today, because that's going to take us maybe a while, like a week or something. And by the way, there is no calculator that exists that's powerful enough to do all 10,000 calculations. The supercomputer UCSD can't actually do all 10,000 because the numbers start getting astronomical and you can't store them. So maybe that's not a good way to go. What about this? I'm going to lose. Oh, the probability of winning is 1 in 10,000. What is the probability of losing? Each time I play, what's the probability of losing?
Is it 9,999 over 10,000?
Yeah, because that's the only other thing I can do. I'm either going to win or lose. Now, I'm going to lose. There's no memory. So what's the probability that I lose the next time? Same thing. What's the probability I lose the next time? Same thing. Do you all agree the probability of losing is never going to change? By the way, how many times am I asking you to lose? 5,000 times. So what's the probability you lose 5,000 times? 999 over 10,000. 5,000 times, and I'm going to multiply that 5,000 times. So how about I just raise it to the 5,000th power? This is the probability of losing every single time. So what's the probability that I win at least once? 1 minus. Let's calculate that, shall we? 1 minus 9999. 1, 2, 3, 4. I'm going to raise that to the 5,000th power, and even a cheap calculator can do this one. And my probability is approximately 0.3935. Now, introduce a little notation. This is not an infinite decimal, by the way. It's a terminating decimal, but it's got a heck of a lot of decimal places. In fact, how many decimal places does this have? Does anybody know exactly how many decimal places this answer has? You actually do. You learn this as kids, believe it or not. Look at how many zeros. So right there, that's a 5 decimal place answer times 5,000. So this has exactly 25,000 decimal places. And it's a terminating decimal, by the way, that's 25,000 decimal places long. Remember, if you had a 2 decimal place number and you multiplied it by another 2 decimal place number, you have a 4 decimal place number. If you multiply it again, you'd have a 6 decimal place number, and so on. This would be a 25,000 decimal place number. So I don't really want all 25,000. This is not a rule, but this is kind of the universal standard with probability. And if you've had stats, you probably already know this. Generally speaking, when calculating a probability and you want to report your answer as a decimal and not a fraction, I could report my answer as a fraction, but it's really big, again, because I have 10,000 to the 5,000th power is a really big denominator. Okay, so I want to report my answer as a decimal. The universal accepted, I don't want to say it's a rule, the accepted answers in probability generally are always 4 decimal places. If you look at your Z tables in a stats book, they're all listed to 4 decimal places. Okay, so 4 is kind of the universal standard if you're going to round a decimal. It's not a rule, but it's a very, very common way to remember things. Now, I'm rounding. It is not equal. Okay, whether you know this or not, there is only one symbol that has ever existed for approximation. Approximation means I am rounding. Generally, approximations only apply to irrational numbers, but in this case, they apply to probabilities because it's too big to write down. Squiggle means asymptotic and is not used in any context if you have one of these. Asymptotic, that means pi is pretty close to 22 over 7. We use a squiggle. That's called estimation when it's a number. There is no estimating in this class. Estimating in calculus would be the tangent line leaves the curve, and I estimate a value on the curve by using the tangent line. That's where the squiggle comes in. It also is mainly used for Taylor series. I'm using a polynomial to estimate e to the x or sine x or cos x because they're asymptotic in nature. Yeah, if you're using a squiggle, that's absolutely an incorrect symbol. And a squiggle means you are saying no decimals are considered correct. It's ballpark, in the neighborhood of. If you're using a squiggle, you're actually saying, don't trust anything I just wrote. It doesn't equal, and it's not an approximation. It's a ballpark figure. That's more like saying pi squiggle 3. That's not incorrect, but it's not useful. So this says that, the probability that I'm going to win at least once is actually not terrible. It's not great, but it's not terrible. I mean, you were thinking of a number very close to 0, for example. So this is called the probability of at least once. And at least once is very specific because the complement of at least once is none. And to calculate the probability of none is usually a simple thing. Okay, so I'm going to flip a coin. What's the probability that I never get a tails? That's not a difficult thing to calculate. So one of my favorite areas where this was used, believe it or not, you may not realize this, one of the scariest movies I have ever seen. Some of you may have seen this, although it's been quite a while. One of the scariest movies I've ever saw was a movie called Super Size Me. I'm curious. Say it out loud. Just say out loud. How many have ever seen that movie, Super Size Me?
Yeah, I have.
Yeah, I've seen that one.
It's absolute. Would you say it's one of the scariest things you've ever seen? It's a movie about a guy who he's doing an experiment and he's going to eat nothing but fast food for, I think it was like a month, and then keep track of all the things that happened to his body as a result. And then he goes into what was going on in all the public schools in the United States and the kind of food they were serving. It was terrifying because it was true. So this guy does this, but what he would do is he would go into a particular restaurant. I won't mention the names because we don't want any lawsuits, but he went into a particular restaurant that would ask him every time he'd go in, do you want to supersize your meal? Or if they asked him, and he'd automatically say yes. And it turns out it was company policy at this particular restaurant to ask, they would say every 5th customer. And it was a random thing where literally there was a counter behind the counter and they didn't ask. And then they'd ask you, do you want to supersize your meal? Which I guess meant huge drink and huge everything. So he would automatically say yes, but he did this and kept track. And he found out that he was actually getting asked a lot more than the company policy said. So I love using this example. If you're asked, do you want to supersize your meal? Let's say 1/5 of the time, okay, you are asked. Then the question is, you're going to go back to this particular place often. Let's say many, many, many times. And so you'd like to know if they're only asking 1 out of 5 times, if I go a lot, I can ask what's the probability of getting asked exactly 1 time or 2 times or 3 times and so on. But let's just say I want to know what's the probability that I get asked at least once. So in 10 visits, I'll keep it simple, find the probability of being asked at least once. That means find the probability that you were asked 1 time, 2 times, 3 times, 4 times, all the way up to 10 times. But rather than doing 10 different calculations that are all actually not that trivial, okay, those who've had statistics, you understand this, okay, there's a lot going on here. All I have to do is calculate, well, what's the probability that I never get asked? So if 1/5 is the probability of being asked, I'll put ask, then the probability of not being asked would be 4/5.
4/5.
1 minus 1/5. I want to know what's the probability that I am not asked every time I go. Now, here's the idea again. Each time I go, it starts over. They're not remembering me. Maybe I'm going to different restaurants. I go, I have a 1 in 5 probability, 1/5 probability of being asked. Now, the next time I go, it's still a 1/5 probability. It didn't change based on anything that happened before. Okay, that confuses folks a lot of times. Nope. In fact, if I'm going to a busy restaurant, they're not going to remember me anyway. Or if they do remember me, they're certainly not going to remember if they asked me last time. Okay, so I want to not be asked how many times? 10 times. So 4/5 to the 10th power, that is the probability that I was not asked all 10 times. So what's the probability that I'm asked at least once? 1 minus. So let's see what that comes out to be. Okay, so if the probability being asked is only 1/5 and I go 10 times, what's the probability I'm asked at least once? Approximately 0.8926. Whoa. Probability is pretty high that I'm going to be asked more than once. If I said, what's the probability I'm never asked? Well, obviously 1 minus this, just a little over 0.1. So this type of probability, it's very, very useful. Again, I said later, if I said, what's the probability you were asked exactly 3 times, we will be able to calculate that probability, but that's a lot more complicated. And that involves math that we haven't even been shown yet. We're actually going to learn that next day. Okay, so what we got today so far, if nothing else, we have the probability of unions. We have probabilities when we have with replacement versus without replacement, and then the probability of at least one, which is a special case, but extremely useful. Now, the last thing we're going to look at today is one of these simpler concepts. Okay. And then I'm going to put it together with a problem later on. You'll like it, a cool calculator problem. Talk about something called the pigeonhole principle. Now, the pigeonhole principle is kind of a funny name for a math concept. It actually has to do with pigeons. So from what I understand, the origins of this, think of the roof of a tall building in New York, right? On the roof, a lot of times they have all of these places where the pigeons will roost, little, not hen houses, but little pigeon houses, I guess you'd call them. And each one has a hole and a little stick sticking out where the pigeon will go and it'll sit on there and maybe duck into the hole and all this sort of thing. So the idea is, if I have more pigeons than I have little pigeon houses, they're called pigeonholes. If I have more pigeons than pigeonholes, there's got to be then at least one of these pigeonholes that has 2 pigeons. Like, this is kind of the most duh theorem that maybe in all of mathematics. So if I have 10 pigeonholes and I have 20 pigeons and they're all coming to roost, at least one of them has got to have at least 2 pigeons. Now you might argue several of them might have 2 pigeons. Well, no, I actually might have one, and then all the rest on the last one. It just means there's going to be at least one. Now, an easier way to think about this in terms of functions. I have a domain, I have a codomain, okay? And I have elements in the domain, I have elements in the codomain, okay. And excuse me, think of this in terms of a mapping. I have a finite domain, I have a finite codomain. That's very important. So I have a finite list of ordered pairs that I'm working with. If the number of elements in the domain exceeds the number of elements that I'm using in the codomain, then there's got to be at least one element in the codomain that gets mapped to by multiple elements in the domain. By the way, that doesn't violate being a function at all. What that does mean is my function is not one-to-one. Okay, remember, one-to-one means everything here has a unique preimage. So if 2 things get sent to the same thing, graphically speaking, that would mean I'd have 2 points that are horizontally located. That doesn't violate being a function. That just means it's not a one-to-one function. Okay, so that's what the pigeonhole principle says. I have more pigeons than there are pigeonholes. There's got to be at least one pigeonhole that has 2 pigeons. It's a really simple concept, but it also helps us do sometimes really, really big problems and answer them clearly. So I like using birthdays. Birthdays is a great one. All right. So let's suppose every one of you actually knows the day of the week you were born on. Okay, that would be hard for most. We'd have to go back and look at a calendar, but let's just pretend all of us know the day of the week we were born on. Okay. Now there's only 7 days in the week. All right. So there are 8 people in a room. And the question is, must there be a day of the week that, and I'm going to put in parentheses, at least 2 people were born on. Assuming everybody knows the day of the week they were born on. I got 8 people in a room. Must there be a day that at least 2 people were born on? What do you think?
No. Yeah.
I'm not saying at least 2, there's at least 2 people that were born on a Sunday. No, I'm not picking the day of the week. I'm just saying, is there a day of the week that at least 2 people must have been born on?
Yes.
Let's look at the most extreme case. The first 7 people I asked were all born on a different day. The first 7 people were Sunday through Saturday. What about that 8th person? What about that 8th pigeon? Do they have to join one of the other people? In fact, I have a line. I have the Sunday lines here and the Monday lines here, and I put everybody stand in the line, and the first 7 people all stand in different lines. But doesn't the 8th person have to stand in one of the lines that's already occupied by a person? Yeah. So we'd say yes, and all you have to say is yes by the pigeonhole principle. You don't actually have to go into explanation. The pigeonhole principle, because there were more things in the domain than in the codomain. I had more pigeons than I had slots to put the pigeons in. There's only 7 days in the week and I had 8 people. Okay, now here's a different question. How many people would I need? Same thing, I've got the days of the week. So the question is, how many people are necessary to, how about guarantee? I like using that word. To guarantee there is a day of the week with at least 4 people born on that day. How's that? All right, think about this one for a moment. You got the days of the week. I want to know how many people am I going to need? The minimum number of people I need to guarantee there's a day with 4 people. The pigeonhole principle was, at least one thing had 2 pigeons. Now I kind of want at least 4 pigeons in one. Now this is not complicated mathematics. Anybody think they know the answer?
Is it 22?
Why?
Because in order to have 3 people per day, you need to multiply 3 by 7, and then you just add 1.
Okay, so if I had 21 people, do we all agree it's possible that every day of the week had exactly 3 people? That's a possibility. Remember, I said guaranteed. Now, from a probability standpoint, if I had, 15 or 20 people, there's a high probability 2 people are born on the same day of the week. I don't want high probability. I want a probability of 1. I want a guarantee. Okay, so the easiest way, Joseph's answer was 22. And here's an easy way to think about it. There's 22 pigeons. There's 7 holes. That's greater than 3. I am now guaranteed, by the way, I can't have a decimal number of people. So the fact is I have the pigeons to the pigeonholes in this case exceeded 3, which means I'm guaranteed there's got to be a 4 somewhere. But if I only had 21, it is possible that there's 3 in every position. And most of you say, oh, that's a no-brainer. Okay, that's so easy. Now, where we get confused on pigeonhole principle often is the probability being high and the probability being 1 are not the same thing. Okay, so if I have, I'm gonna do it a different way. We're gonna continue with days of the week because that's really simple. There are 7 days in the week. All right. In a room with, let's say, just do 4 people. I want to find the probability. Actually, let me go 5 people. I want it to be higher. A room with 5 people, find the probability. Whoops. that at least 2 are born on the same day of the week. Can I guarantee, if I've only got 5 people, can I guarantee that at least 2 are born on the same day of the week with only 5 people?
No.
No, we said it took 8 to guarantee. Now, by the way, I didn't say the day had to be Sunday. I could have 1,000,000 people and not have anybody born on a particular day. Do you agree with that? In fact, I just look at a registry and I'm going to invite all the Tuesday birthdays. All right. So everybody born on a Tuesday, I can have everybody on planet Earth who was born on a Tuesday. And they're all born on Tuesday. I didn't use up the other days. That's not what I'm doing. I'm not selecting a particular day. I'm just saying I got 5 people in a room and I ask each of them what day of the week you're born on. What's the probability that at least 2 of them are born on the same day of the week? And it could be any day. That's what I'm looking at. Now, we know the probability is not 1. Okay, because we said by the pigeonhole principle, the only way to guarantee it was to have at least 8 people. That's how I would get a probability of 1. So how do I calculate this probability? Well, think about it in terms of calculate the not born on the same day. Oh, okay. So let's calculate the probability that none of these people share the same day of the week. And if I do that, then I just got to go 1 minus that to find the probability. Now, wait a minute. I thought it was at least 1. Well, if I have a bunch of people and I say, okay, at least 2 of you have the same birthday. The complement of that is nobody has the same birthday. So wait, wouldn't it be at least 1? No, 1 person having the same birthday as themselves. That doesn't work. So in other words, I said, okay, 2 of you or more have the same birthday, or nobody has the same birthday. Does that make sense? In this case, the least is to have 2 or more people have the same birthday. So me and AJ have the same birthday, or we don't have the same birthday. You don't say I have the same birthday as me. There's 1 other person I have the same birthday with. So that means 2 of us have the same birthday, or none of us have the same birthday. So we want to calculate what's the probability that no 2 people have the same day. So regardless of whatever the first person is, there's a 7/7 probability they have the same birthday as themselves. Okay. What's the probability that the next person selected, okay, does not have the same birthday? Well, that would have to be 6/7, wouldn't it? Because there's 6 days of the week left. So whatever day of the week I'm born on, there's a probability of 1 that I have the same day of the week as me. Now, if I grab a person at random, what's the probability they were born on a different day as me? 6/7. Okay, now there's 2 of us. Now the next person, what's the probability they have a different birthday than us 2? I agree. 5/7. By the way, it's 7 each time. Okay, I'm not reducing this. Now, the 4th person, what's the probability they have a different birthday? And how about the 5th person? The product of these numbers is the probability that no 2 people share the same birthday of the week. That's it. So what's the probability then that at least 2 people have the same birthday? Let's calculate this, shall we? And by the way, if you notice, there's a way you could do this quickly. My denominator is obviously 7 to the 5th power. What's my numerator? Think the phone number problem we did last day. 76543.
7 exclamation point divided by 2. I don't know what the
Or
exclamation.
how about permutation? Do you remember the phone number problem we did the other day? Oh yeah, 2, 1, 2. I want you to do this as a calculator problem because sometimes these can get really big. So this is my numerator. I can use the permutation key on my calculator, in other words, or I can enter all these fractions. Both are correct. Entering all the fractions is very time consuming. So I'm going to do it like this. So 1 minus probability. Oops, try that again. 1 minus, here we go. 7, 5 divided by 7 raised to 5. Very interesting answer. It's almost exactly 0.85. I've got 5 people in a room. The probability at least 2 of them were born on the same day of the week. It's really big. It's not 1. No, it won't get to 1. Okay, when will it get to 1? We said when there's 8 people. Can you see it from the formula? This is the 5th person. What's the 6th person going to do? What's the 7th person going to do? What's the 8th person going to be? And now I have 1 minus 0. Here's an easy way to show that, oh, an 8th person, the 8th person can't have a different birthday than the first 7 because there's no days of the week left. So if you thought about it that way, you go, oh, okay, the 8th person or anybody beyond the 8th person would guarantee. Now, this problem right here is classic. I love doing this. When I would teach statistics, I would always do this. Before I'd even start the class, I'd say, I will bet, okay, that at least, I would say things like, if I had a big class especially, I'd say, I bet at least 2 of you have the same birthday. Now, I'm in this case, I mean day and month, not year. You know, January 25th, you know, September 2nd, whatever. I'd say, I bet at least 2 of you have the same birthday. And I'm willing to put money on it. Everybody like, you know, laughing. And so then I'd say, okay, let me write on the board. I'd write all the months. And then I just say for January, just yell out, if you're born in January, yell out the day, you know, 3, 7, 13, 14. And I do this across the board. And every class I've ever taught, I had at least 1 pair, if not multiple pairs of people who had the same birthday. And they'd always be blown away going, wait a minute, there's 365, forget leap year. There's 365 possible birthdays. We've got 40 people in the class. How in the heck could you be sure that at least 2 of us had the same birthday? That's not possible. Well, it's not possible to guarantee, but from a probability standpoint, it's absurd, believe it or not. And I'm going to show you. This is often referred to as the birthday problem. It's a classic combinatorics problem that we now know how to do. It's this problem right here. So again, let's exclude leap years because that gets kind of complicated. You know, let's just assume if you're a leap year, we'll just call that March 1st or call it February 20th. Do whatever you want. All right. Find the probability with 40, let's say 40 people that no 2 people. I'm sorry, not no 2. I'm sorry, find that at least 2 people. Sorry, at least 2 people share the same birthday. Now, this will be a mind-numbing calculation, but I showed you a little trick. We can actually make it a really short calculation, as long as you have a good calculator. Now, the problem is you might not have a good calculator. Let me see. Let me see if I can actually do this on mine. Okay, hold on. Okay, you know what? I'm going to change. I'm looking at my calculator. My calculator is, it's not, my calculator is not going to be able to handle the 40. Let me try this. I'm going to change this to 35. My calculator can do 35, but the 40, it didn't want to do. I think that's funny. I can use my TI-89, but I'm not going to, you know, my titanium, but that's, you know, that's intimidating if I pull that one out. Okay, let's say 35 people. I got 35 people in a room and I'm going to make a bet. And by the way, this is a great thing to do at parties. You know, you look around the party and say, okay, and there's a lot of people here. And you bet somebody, I bet you $100 if you're a gambler, that at least 2 people here have the same birthday and I don't know anybody's birthdays. And then somebody's going to take you on in a second and you're probably going to win that bet. And I'm going to show you why. Because so what we're going to calculate is what's the probability that no 2 people share the same birthday. Okay. So the probability of, of no 2 people, or no, I just say nobody. I'm sorry, not no 2 people. Let's just say nobody. Probability of nobody sharing a birthday. So you can basically start like this. I have a whole group of 35 people. It doesn't matter which person I start with. So you select one person. Okay. Now select the second person. What's the probability those two people do not share the same birthday? Now select a third person. What's the probability that none of those three share the same birthday? And by the time you get to the last person, the order you did it in is irrelevant because you've now considered all 35 people. So the first person is going to be 365 over 365. Of course, the first person has the same birthday as themselves. Now I grab a second person at random. What's the probability, without knowing the birthday, by the way, what's the probability that they have a different birthday? That'd be 364 over 365. And then the next person, 363 over 365, and so on. How many times am I going to do this? Well, I have 35 people. So 34 people later would be 334 over 365. Okay. This is the probability now that nobody shares the same birthday. Is everybody cool with that? The probability no two people share the same birthday. So the question is, what's the probability that at least two people share the same birthday? I now want to do 1 minus this, which will be 1 minus 365, choose. I said 31, I'm sorry. I meant that should be 331, sorry. I'm selecting 35, so 34 people later. To the 35th power. Now that's a mind-numbing calculation, but let's do that on our calculator. So I'm going to go 1 minus 365 permutation 35. That's why I showed you the thinking of that as a permutation. Hopefully my calculator can handle this. It did. Oh, that was fast. And here's the thing that might blow you away. I've only got 35 people in a room. The probability that at least two of them have the same birthday, this is why I would make that bet. If you were, a gambler and you said the probability that you're going to win your bet is better than 0.8, I think you'd feel pretty good about that bet, wouldn't you? Wait, but there's only 35 people in a room. Yes. And every additional person in the room, this is going to go up. Now, when I have the 366th person in the room, see, if I keep going, eventually I'm going to have this, and then the 300, that's the 365th person. And then the 366th person, there's no days left. That's when I would get a probability of exactly 1. By the Pigeonhole Principle, I would need at least 366 people to ensure that at least two people have the same birthday. Not the particular day, just at least two people are going to share the same birthday. Absolute guarantee, 366. But it turns out I don't need very many people to have a high probability. Now, for anybody who's ever seen this before, the question people always ask is, so how many people would I need to have a probability greater than 0.5? You see, if you're going to gamble, you want to know that you're going to win more likely than you're going to lose. So if the probability is greater than 0.5, then I'm more likely to take this bet. Does anybody know how many people you need to have a probability greater than 0.5 that at least two people have the same birthday? If you've ever done this problem, you may remember the answer. Anybody want to take a shot? $23. Yeah, let's do it. Put 23 in there. 1 minus 365 permutation 23 divided by 365 raised to the 23rd power. Isn't that crazy? If I have 23 people in a room, the probability that at least two of them have the same birthday exceeds 0.5. Yeah, like I said, it doesn't always make sense, but remember, these things are getting smaller as we go. So this is a really cool form of probability. The probability of at least, because using the complement of none, that's really what we're looking at here. I am not interested in the probability of 5 people sharing the same birthday. That's way more complicated. but at least two people having the same birthday, because the complement is nobody has the same birthday, and the complement is generally easy to calculate for these problems. Okay, so that's kind of, again, the mix of the pigeonhole with the probability is key, that we understand the difference. So, okay, so we have an exam on Mondays, everyone knows, and the exam goes through lecture 16, which is also quiz 16. Let me grab the syllabus here. Okay. The first exam, of course, was the first 8 lectures. The second exam is the next 8 lectures. And a common question that is asked is, are there going to be questions from the first exam on the second exam? No, no. You're accumulating knowledge as you go, but you're only going to be tested on the next 8, which if you look at your quizzes, are quizzes 9 through 16. Now, the cautionary tale that I want to present is, and my Calc 3 people just had an exam yesterday. And right now, the most missed questions on their exam are by far the simplest questions on their exam. It's not even close, but it's the material from the first couple of lectures. You say, why would that be so hard? The first lecture you're being tested on was March 3rd's lecture. March 3rd was like a year ago. Okay, the exam material starts on March 3rd. That was so long ago, and we had a spring break in between, that people forget to go back and look. So the absolutely easiest stuff, this didn't even involve calculus. There was a couple of questions that anybody could do with remedial algebra that people are missing and actually leaving blank on my calc test because they didn't go back and look at it. And they didn't realize how long ago the material was covered. So I got to caution folks on, go all the way back. One of the crucial mistakes people make is they go, oh, I got 100% on that quiz, I'm good. Yeah, but if the quiz was 6 weeks ago, do you really remember it that well? So a good rule of thumb is not just to do the practice test, but to retake all your quizzes. That's why I put the keys online. I don't do that for my benefit. I do that so you can test yourself. Go back and retake them. If you missed them, have you figured it out? But far more importantly, if you got it right, do you still remember? That's actually way more important. People just take it for granted. Oh, I got 100%. I'm going to get 100% on the exam. I haven't done it in 6 weeks. That's iffy. Okay, because we move around topic wise, so there's no guarantee. So that's why you want to go back and look. So as always, the exam, I'm going to email you the exam about 10 minutes early, and I will send you an email over the weekend reminding you that I'm going to email you the exam a few minutes early. So either print the exam or you can write the questions down. If you can print the exam, that makes your life so much easier, because first of all, you don't have to take the exam staring at a computer screen. But if you don't print the exam, you've got to take the entire exam with your nose to the screen. And I personally, I don't like that because I think it's really bad for your eyes. Plus, there's always the possibility you miscopy the question when you're writing it down. That's a totally separate issue. What can you bring? Like last time, a 3x5 card, both sides, with theorems, formulas, definitions that we have learned in this class. There's nothing from another class that's going to help you anyway. We're not doing calculus. But if there's things that you're not absolutely certain about, okay, the rules of Boolean algebra, for example. I mean, what is the distributive law of unions and intersections? You know, things like that. You know, what are they? The De Morgan's laws. Some of the ones I know you know because you've seen them so many times, but the Boolean algebra with the pluses and the times and the bars over the top, that's an area that was, you know, a little confusing. What's the definition of reflexive, symmetric, and transitive? Now, what you can't do is have examples written down, because that's making it open book. It's not open book, and every question on the exam you've seen before. But for example, if I'm asking you something with the Euclidean algorithm, you know that's trivial. That is actually, and I'm not exaggerating, that's like 3rd, 4th grade level of arithmetic. Why? You're subtracting, finished. But it's the algorithm that you got to get right. You have to know what order to do things, because even though the arithmetic might be trivial, okay, it's an algorithm. So if I make any mistakes along the way, it will change my answer. There are proofs. There are proof by inductions. Of course, there are proof by contradictions. Not complicated. Oh, no. Especially at like the induction proofs. Very, very simple, straightforward. And I've given you more problems than you have to do. Okay, I've given you a choice. So I might give you 8 proof problems and say do 4 of them or something like that. So you have some options. And in fact, I think the way I did it was I did not put an extra credit question on the exam. On the proof-oriented questions, if you choose an extra one, that you can use that as your extra credit. Okay, not that they're super hard, but they generally take a little bit longer. And so they're more taxing. That's why I'm not asking you to do every single one of them, because I want you to be able to finish the test. But there's div and mod, right? Equivalence classes, some of that stuff, again, not difficult, but it's stuff that you may never have seen until recently. And so therefore you might not know it inside and out. So that's why theorems, formulas, definitions. On this test, it's probably more definitions and theorems. I don't even know if we have technically formulas. Now, exam 3, it's all based on this chapter. Exam 3 is going to be nothing but formulas. Okay, I mean, we've already looked at formulas today, but they're not complicated, but that's down in the future. You're not calculating for the most part, but you are going to be doing Euclidean algorithm stuff. So please have a cheap calculator on hand. Don't do that pencil and paper. Oh my gosh, you understand it, but you made an arithmetic error because you did it in your head. I know it's funny, but at this level, and I still have to, I battle this all the time in linear algebra and differential equations. At this level, people think a calculator is a sign of weakness. If I have to use a calculator, I shouldn't be in this class. I'm above calculators. Not for arithmetic, you shouldn't be, right? You know the concept, but you can't afford to make arithmetic mistakes. Have the calculator there to do the subtraction so you don't run the risk of doing something incorrectly. You know the concept. You got to get the answer right because you know how to do it. Again, arithmetic errors. And I think the Euclidean algorithm stuff is probably the only place where there is going to be a potential. Okay. Now I'm gonna take a break. Unless real quick question, Joseph, because we're gonna do office hours, and that's where we're gonna go over practice tests and stuff. Do you have a quick question?
Yeah, I had a question about those 8 problems. What if we do all of those problems? Could that be bad?
Yeah, that's a good question. I would rather you didn't, because from a time standpoint, if I say there's 8, do 4, and you do all 8, from a time standpoint, you're cutting into the time to perhaps finish the test. Now, flip side, you did 4, you finished the test, you checked everything, and there was still time on the clock. Oh, and then absolutely go back and do extras. But I think those occur relatively at the beginning of the test. And my fear is if you do every problem, you don't have to, and they take you some time, you see the problem, you run the risk of not finishing the test, and you did problems that aren't even going to count. It is always wise. And I say this in every class I teach. If I say select from a group of problems, do the minimum number I suggest, then after you check, if time allows, always go back and do an extra. That's called insurance. So if I said do 4 and a 5th one will count as extra credit and you have time, then how many should you do? 1 more.
You won't get, I can still do those other 3 if I'd like for learning, but
Yeah.
you won't count those. You won't count those.
But again, it's a time thing. That my fear is if you take the longest problems and you do all of them, are you going to have time to finish the rest of the test? It's okay to do that, but only do that after you finish the test and come back to them. Does that make sense? No, in other words, only do extra problems if you have time to do extra problems. Don't do them in lieu of the problems that are going to count. That's my fear, is that some people will do that. They'll do every problem all the way through, even the ones I said choose, and then they get to the last portion of the test and they can't finish it. You know, that's not a good idea. That's not good test taking strategy. Good test taking strategy is you do the minimum number you have to do and you check them. And if there's time on the clock, now go back and do an extra. Now, if you say, well, should I do all of them? No, and here's the reason. I don't even remember how many I said to do, but let's say I say do 4 out of 8. That 8th one, it's probably not very good. Why? Because you put it off till the 8th one for a reason. You put it off till the end because it was the one you had the least confidence in. Oh, I still have a few minutes. Let me try that one. That's not going to count. Now, every now and then, you know, I'll have somebody where nothing challenges them. And it doesn't matter which ones you did. You can do all of them. Well, that's great. You know, you can show off if you want. But I'm more concerned with you finishing the test than doing problems that aren't going to count. It's absolutely okay to do problems that aren't going to count, but make sure you finish the test first. That's all I'm saying. Because I don't want you to have perfect answers to things that don't count and then blanks at the end of a test. That no work. All right, let's take a short break.